approximately. Well, I'm booked. What are you doing tonight? I put in my study times. Oh. We can move this one later.
Your study time?
Yeah. At approximately 6:30. Would you like to go?
Yes, ma'am. 6:30? Wait, let me check my studies. Okay.
Or else I'm not doing that.
I don't have to, so I need to really.
You got to put it on your calendar to do it.
Yeah.
I didn't see this.
I put my to-do list here too.
Yeah, I just have to phone.
Yeah.
And I schedule times that I'm gonna do certain times. I don't schedule
Or no, like this is my time to do that exact time. I didn't put my stuff in the lunch either.
Yeah, you can wear it.
And then I think she just disappeared. She disappeared and later, I wasn't able to talk to her. With her It's not so much the sinus infection anymore, but it's just my nose is stuffy now. Yeah, so that's kind of putting way too much time into it.
All right, so we're starting by working on this problem we talked about at the end of class. So if you did stuff over the weekend, this will feel like, okay, maybe a little challenging, but I got it. If you didn't, it's going to feel hard. So that's a good indicator that you need to. I was going to say that you need to do some practice problems, not like you have a choice because your homework is due tomorrow. So a good reminder. Remember we said when you first look at this one, your inclination is like, I need 1 mole of H2 on the reactant side. Don't start there because you have H2 in both of these and it's going to be confusing. So start with the others and just kind of see where you can go from there. Okay? And I know I forget this all the time, so I do have it today. It looks like in this class I haven't sent it around since the beginning of the month. That's pretty pathetic. Okay, so let's talk through this. Skipping over H2, looking at Cl2. Reaction 3 is the only one that has that, and it's in the right place. There's 1 mole of it on the reactant side. So I'm just going to make a note over here that I'm going to leave it as it is. So I'll write whatever I'm going to do to the delta H, like times -1 or times -2 or whatever the case is. I'll write that down, knowing that I'm going to do the same thing to the reaction, but I'm not going to like go ahead and write down all of the reaction details and manipulate them until I feel like I have a pretty good idea of where I'm headed. Okay, so I just jot it down so that I know where I'm going. All right, next one, HCl. I need 2 of them on the product side. So reaction 1 has HCl. It's only 1 mole though, and it's on the wrong side. So I'm going to flip it so that it's on the correct side, and I'm going to multiply it by 2. So I've gotten the 2 things that I want, and I still don't know what's going to happen with those H2s, because if I used reaction 2 to try to get it, like if I did a third of that, then that's going to start getting weird, because what happens with those 4 H2s? So I'm just going to go ahead and write down what I have so far and hopefully figure out how this is going to pan out. I know I'm probably going to have to use reaction 2, or else why would it be there? I just don't quite know how yet. Okay, so I'm going to take that first one, flip it, and multiply by 2. So 2 NH4Cl, 2 NH3. Like already, you should notice that I'm writing down compounds that I don't have in the final reaction. So I do need to cancel those out at some point. Like I can't leave them in there. But let's just kind of finish what we've said we're going to do so far and then see where it goes. So, okay, I've got my 2 HCl's, so that's good. And then I'm going to do the manipulation of reaction 3. Well, not manipulating it because it just is as is. So I'm going to write it down. N2, 4H2, Cl2, 2 NH4Cl. Okay. Oops, I forgot to write down the delta H's here. It's an important component. Okay, so for the first one, the delta H was flipped. So now positive times 176, so 75, 150, 250, 352. That was me multiplying by 2 in my head. I'm sure you guys really wanted to hear that out loud. Assuming that it's right. No, 4 should be 452. No, it's 3. Okay. All right. And then the next one didn't change, so we'll just write that down. Negative 629. And now it's like, where do we go? So wait, first let's circle this. Okay. So we can cancel out stuff that cancels out. That's a good place to start. So the NH4Cl, those cancel out. And now I'm left with nitrogen, 4 hydrogens when I only wanted 3, and 2 NH3s on the product side. So when I look at that second reaction, I can either think about it, the easiest thing is think about it in terms of the nitrogen or the NH3. If you really want to, you can figure out how the H2 is going to work, or else it'll just figure itself out if you use the others. So I don't know, whatever. I'll think about the N2. So I need to get rid of the N2 that's on the reactant side, which means I need to flip this reaction so that there's one on the product side to cancel it out. In the process, that's going to move the 2 NH3s to the reactant side so that those will cancel out. So I am going to flip this reaction. Same number of moles, but just turn it around. So 2 NH3 forming N2 and 3 H2. So now the NH3s cancel, the N2s cancel, and hopefully you can see 4 H2 and 3 H2. So think of this like H2 and H2 and H2 and H2, okay? So 3 of these guys are canceling out with those, and you're just left with the one behind, which is what we wanted. So now I'm just going to sum them up. Let's see, I didn't do the delta H again. That's positive 92. Okay, so I'm going to sum them up and make sure I have everything I want. H2, Cl2, and 2 HCl. So I have everything I want. I don't have anything I don't want. And now I'm going to add those together. And I get negative 185. Okay, so like I said, use this as a gauge of your preparedness, you know, understanding of the material. If you did some stuff over the weekend and now this, like you understood how to do this, you're probably good. You can finish up the homework, do the practice exam, you're good. If this felt difficult, you probably just need to do the homework and do more practice. And like I said, if you need additional beyond that, you can start in on the practice test. Okay? All right. Any questions about this one? All right. So the next stuff we're going to do is actually related to this. Remember, this is called Hess's law, this manipulating equations to make them look like the one we want to get. The stuff we're going to do is based on that, but it's using a very standardized set of equations. So let's start there. The standardized set of equations, they come in tables. This is like an abbreviated one. There's 3 pages worth of them here so that we can use them in the problems we're going to do. So when we look at these tables, they're just a chemical, and then it says delta H. If you notice, it says delta H with this little F subscript, but it doesn't give you a reaction. It just gives you a chemical, okay? So what these actually mean is they are showing you the chemical because the equation itself is very clearly defined. Sorry, that was the wrong slide. So this is what the equation is. It's going to be to form 1 mole of that compound. So let's say we looked up CH3OH, and it says the delta H, this little F, it's called the delta H of formation. So that guy's right here, negative 238.6. Okay, that's to form 1 mole of the compound. So 1 mole of CH3OH, forming it, meaning it's a product. And it says from its elements. Okay, so what elements make up CH3OH? Carbon, hydrogen, and oxygen. But it says in their elemental form, okay? So elemental form means if it's diatomic, you need to make sure you write it as diatomic. If it's not, then don't. Just write it by itself. So carbon should just be by itself. Hydrogen and oxygen are both diatomic elements, meaning if they're by themselves, they come in a pair. They won't just come H or O. If you forgot which ones those are, starts with hydrogen, then picture the periodic table. Over here, you've got like nitrogen, oxygen, fluorine. It makes a little 7 on the periodic table. There's 7 of them. It's another way to remember it. Cl2, Br2, and I2. Okay, so it's the halogens, hydrogen, nitrogen, oxygen. Okay. Problem with what we've written so far, though, is that it needs to be balanced, okay? Normally, we would put a 2 here because there's 1 oxygen and we need to have 2 oxygens on that side, and we would go through that process. But we only form 1 mole. Like this enthalpy is for 1 mole. So this is one of the rare times when we let you use fractions. So we need 1 carbon, done. We need 4 hydrogens, so we'll put a 2 there. And then we just need 1 oxygen, so we're going to put a half there. Okay? So that is the reaction it's talking about when the table says the delta H of formation of CH3OH is negative 238. This is the reaction it's talking about. Why don't you do another one for me? Do nitric acid, okay? So write the reaction that would correspond to the delta H of formation for HNO3. I'll go look up what the value is. It might not even be in this table. Looks like it's about 206, negative 206. Most of these are negative because most compounds, when they form from their elements, will release energy. Some of them are not. So your elements are all diatomic, actually, hydrogen, nitrogen, and oxygen. So then you need to balance those. So that's what that one would look like. And there's a couple other examples on the next page too. Okay, so the only other thing with this, you'll notice when you look at the delta H of formation, you see it down here, it has this little 0 or degree sign or whatever you want to think of it as. It's telling you, so we can't tabulate these values for every single temperature and pressure. So we set a given temperature and pressure to report the value at. So it's 25 degrees C, which is basically room temperature, 1 atmosphere of pressure, and then if it's a solution like salt, water, or something, it would be 1 molar concentration. Okay? We just have to have a standard way of doing it. So that little circle means standard states, these standard states. The other thing is you need to pay attention to the physical state. You guys won't have to predict those. It will be listed in the reaction itself, but you need to pay attention to them because like water in particular will be included as liquid water and gaseous water in these tables, and they have different enthalpy values because it takes a certain amount of energy to turn a liquid into a gas. So those are going to be slightly different. So just keep that in mind that you do need to pay attention to the state when you're looking at it. Okay? All right, so what are we going to do with these? The whole point of this is that these are the known equations we're going to use and then manipulate to make look like the one we're trying to get to. Okay? So come down, skip over that page. We're going to come back to it. So this is the benefit of not being the first class. There should be a 2 here. We got like halfway through the problem, and I was like, why are these not canceling out? Well, because the equation's not balanced. You can't do a problem, you got to start with a balanced equation. Okay, this is the equation we want to find the delta H of. All right? And these are the delta H of formation equations that we're going to use. Now, I could have, like, just said, use the ones from the table for CH4, CO2, and H2O, but I went ahead and, like, gave you the reactions themselves. So what I want you to do is take those equations and do another Hess's law problem and figure out what the delta H is for this equation above. Okay, so just like we did at the beginning of class, manipulate these ones, make them look like that one. Don't worry about the whole graphite thing here. I mean, it's going to cancel anyways, but you don't need to worry. It's just saying the form that it happens to be in, because energy between graphite and diamond, even though they're both carbon, is going to be significantly different. Okay, so I've put up there the manipulations that I can tell I need to do, which ones I need to flip, and what coefficients to multiply them by. So I'm going to go ahead and do that and make sure everything comes out the way I want it to. Why did that not come out like I expected it to? I must be remembering a different one. So I'm getting negative 802.5 for this one. Okay, good news. You don't ever have to do it this way again for these problems. When they are the standard enthalpy of formation, what happens is that because you're using the same elements on all the different reactions, they will always cancel each other out. So all you have to do is, all of the compounds are on the product side. So all you have to do is flip them if they're on the reactant side, and then multiply any of them by their coefficients. Okay, so the way we say that in an equation is you're going to do the sum or add up all of the delta H of formation, but multiply them by any coefficients. So like we just did, we did 2 times water plus CO2, right? Those delta H's of formation. And then you're going to subtract the one for CH4 times its coefficient, but it was just 1. And then you'll notice we didn't include the oxygen there. I can put it in there, the delta H of formation of oxygen, but guess what? Is it listed there? Let's go down here. Look at all these zeros that appear in the table. Calcium, carbon, Br2, sure oxygen's in there somewhere. Oxygen. That's because they're already in their elemental form. Forming 1 mole of O2 from its elements in their elemental form, there's no change. So if it's already in its elemental form, you can look it up in the table, but it's going to be 0. Okay? So we take the H2O, times it by its coefficient, the CO2 times by 1, subtract, and the reason why we subtract is because we're flipping it. Okay? So this is on the exam equation sheet. You can just remember it as products minus reactants, as long as you know that you've got to multiply them by their coefficients. Okay? So you don't actually have to go the long way. You can do it this way. So we're going to do 2 more problems that are just like that using this equation so you can practice doing it. And we could go ahead, I think in my other classes I did this. We go ahead and prove it. It comes out to be the exact same number, the 802. The reason why that works is because what you're basically doing is you're taking your reactants and you're breaking them up into their compounds. This is something, their elements. This is something we sort of talked about when we talked about the source of enthalpy has to do with it takes energy to break bonds and then it releases energy to form bonds. This is pretty much that, although you're going to its elemental form, so you're not literally breaking all of those H2s up. So you're taking the reactants, you're breaking them into their elements, and then you're putting those elements back together into the products. So it's like you're summarizing that in these different reactions. In the CH4 one, you're breaking it up into its components, and then you're putting those back together into the reactants. I just said reactants, products. Okay, so let's do an example where you just use the equation. Don't worry about writing them all down. So these 3 pages, you'll need those to do the problems. And for some reason, I'm missing the states on this, which normally wouldn't matter that much, but we've got water in there. Let's go with liquid on this one. And then on the next one, I'm going to do all of those as gases. Well, not the ethanol. Okay, so take note that it's water liquid. So use the equation and the tables to determine the enthalpy of this one. Okay, so I'll write it out symbolically and then come back and plug in numbers while you guys are working. So I'm just pulling all these values from the table and plugging them right into that equation. It doesn't look familiar. Let me double check that I didn't miss a number in here. Probably because I did gas in my other class and not liquid. Yeah, I think that's why. Okay, a minute or so to look it over and then let me know if it's causing any issues. So I kind of think the calorimetry ones, these ones are probably pretty straightforward. You just need to do them a couple times to make sure you don't mess anything up. And then those Hess's Law ones and the concepts, maybe a little bit more time on those. I have had people say that now that they go back and read the concept stuff, they're like, okay, this makes sense. Like, it's not crazy. It's just easier once it's has some calculation context. All right, one more. Okay, so this one has two parts. You're going to find the delta H, and then you're going to use it in this above stoichiometry problem. So I'll start doing it up here if you want to follow along. Well, let's see. So I've got the enthalpy up there, and now I'm doing the stoichiometry part. Oh, well, that's wrong. Okay, so good reminder on this that when you find those delta H values, those are for the reaction as written. So if you're adapting it to a different amount than just 1 mole in that instance, then you need to do a stoichiometry problem. Also keep in mind, if this was like for 4.77 grams of CO2, then that would be a 2 CO2 for every negative 1, 2, 3, 4.8. Right? Because that's the coefficient in the equation. So the ratios have to match up just like the coefficients and then the enthalpy, just like if we were doing, you know, a stoichiometry problem just with the ratios. Okay? All right, that's all I have. So I'll see you guys on Wednesday. Don't forget the homework and the reading for Wednesday. Yeah.